Good morning. Welcome to the session. Today we are going to discuss about the topics VSB modulation, that is vestigial sideband modulation, frequency domain description of VSB modulation, generation of VSB modulated wave, demodulation of VSB modulated wave, frequency translation, frequency division multiplexing, the MCQs related to today's session and MCQs link through which you can take a test. VSP modulations. See, the SSP modulation is not appropriate way of modulation when the message signal contains significant components at extremely low frequencies. Because in such cases, the upper and the lower side bands meet at the carrier frequency and it is difficult to isolate one sideband. To overcome this difficulty, the modulation technique known as vestigial sideband modulation is used. And also, when a sideband is passed through a filters, the bandpass filter may not work perfectly in practice, as a result of which some of the information may get lost. So to avoid this loss, a technique is chosen, which is a compromise between DSBSC and SSP, that is double sideband suppressed carrier and the single sideband modulation, called as vestigial sideband modulation or vestigial sideband technique. The word vestige, which means a part from which the name is derived. Vestigial sideband modulation or VSP modulation is the process where a part of the signal called as vestige is modulated along with one sideband. Along with upper sideband, a part of the lower sideband is also being transmitted in this technique. A guard band of very small width is laid on either side of VSP in order to avoid the interference. This guard band in the sense it is the gap between the upper sideband and the lower sideband. VSP modulation is mostly used in television transmissions as these are having low frequency ranges. So this is how we we shifted from SSB to VSP. Now we will see frequency domain description. Frequency domain description. So this is the spectrum of the VSP signal, message signal and the VSP signal. Spectrum of the message signal, which consisting of the message whose message signal whose bandwidth is between -W to +W or -FM to +FM. Here you can see the spectrum of VSP signal. So this VSP signals is consisting of a full, see here we are transmitting a full USB upper side band and a part of the lower side band. See vestigial. Even here also we are transmitting full USB and a part of the LSB. This vestige, that part of the LSB is represented as FV. V stands for the frequency of the vestige. So here figure shows the spectrum of vestigial sideband modulated wave S of t along with the message signal M of t. Here lower sideband is modified into the vestigial sideband. The transmitted vestige of the lower sideband compensates for the amount removed from the upper sideband. The transmitted bandwidth required for the VSB modulated is given as bandwidth is equal to W plus FV. FV is nothing but it is the vestigial frequency. So this is about the frequency domain description. Next, we'll see generation of VSB modulated wave. So modulators, we'll call modulators. Modulators are the devices which is used to perform the modulation operations. So here in wave, this is the generation of VSB modulated wave. Here this modulated wave, this is the block diagram which consisting of a product modulator, local oscillator, sideband shaping filter. The input for the product modulator are M of t and C of t. M of t, it is a message signal, C of t, it is a locally generated carrier signal. And the output of the product modulator, you will be getting DSB-SC wave, that is double sideband suppressed carrier wave. So if you pass this double sideband suppressed carrier wave through the sideband shaping filter, you will get the output as vestigial sideband or vestigial sideband suppressed carrier wave. So we can generate the VSB modulated wave by passing DSP-SC modulated wave through sideband shaping filter. The filter can be designed to provide desired spectrum of VSB modulated wave. The relation between the transfer function h of f of the filter and spectrum s of f of the vestigial sideband modulated wave s of t is defined by S of f is equal to AC by 2 into M of f minus fc plus M of f plus fc into h of f. So this is the output of what is that sideband shaping filter. H of f, it is the transfer function of the sideband shaping filter. So S of f is given this one. And here M of f is the message spectrum. This is the generation of how we are going to generate the vestigial sideband modulated wave. Next, we'll go for the demodulation of vestigial sideband modulated wave. Demodulator. What exactly we do here? Recovery of the original message signal, we'll call it as a demodulation. And the device which performs demodulation or recovery of the original message signal, will call it as a demodulators. Here, the demodulation of VSB wave, it consists of 3 blocks: product modulator, low pass filter, and the local oscillator. So the input for the product modulator are S of t, that is VSB-SC wave, and C of t, that is AC cos 2 pi FCT. So this product modulator multiplies S of t with the C of t and gives the output V of t. So whereas V of t is equal to S of t into C of t. And then this V of t will become the input for the low pass filter. Means when you send this V of t through the low pass filter, we'll get V naught of t, that is demodulated output message signal. What the low pass filter will do? The low pass filter will allows only a low frequency signals and it will reject other higher frequency signals. So in this process, the message signal can be extracted from VSB-SC wave by multiplying it with the carrier, which is having the same frequencies and the phase of the carrier used in VSB-SC modulation. The resulting signal is then passed through a low pass filter. The output of this filter is a desired message signal. Now we will see mathematical representation of this demodulated signal. How we are going to derive it? See, let the VSB-SC wave be S of t and the carrier signal is AC cos of 2 pi FCT. From the figure, we can write the output of the product modulator as V of t is equal to AC cos 2 pi FCT into S of t, because the input for the product modulators are S of t and C of t. So C of t can be represented as AC cos 2 pi FCT. So that's why V of t is equal to AC cos 2 pi FCT into S of t. Applying Fourier transform on both the sides, V of f is equal to AC by 2 S of f minus fc plus S of f plus fc. We know that S of f can be given as AC by 2 into m of f minus fc plus m of f plus fc into h of f. Now here what we have to do, we have to find the values for m of f minus fc and m of f plus fc. So how we are going to find? See, we know the value for, so how? In this case, sorry, yeah, by using this, we have to find S of f. So here, S of f minus fc, which is equal to AC by 2, m of f minus fc minus fc, means we are adding minus fc to this, and we'll get f minus fc minus fc plus m of f minus fc plus fc into h of f minus fc. So if you simplify this minus fc will become minus 2fc. Fc minus fc plus fc will get cancelled. So you'll get S of f minus fc is equal to AC by 2 into m of f minus 2fc plus m of f into h of f minus fc. Now we have to find the value for f plus fc. That's why add s of f with fc. So s of f plus fc is equal to AC by 2 m of f plus fc minus fc plus m of f plus fc plus fc. So minus fc plus fc will gets cancelled. This will become 2fc plus h of f plus fc. So S of f plus fc can be written as AC by 2 m of f plus m of f plus 2 fc into h of f plus fc. So now what we have to do, right now we got the values for S of f minus fc and S of f plus fc. So now substitute the values of these two values in V of f. So we will get V of f is equal to AC by 2 into AC by 2 m of f minus 2 fc plus m of f into h of f minus fc plus AC by 2 m of f plus m of f plus 2 fc into h of f plus fc. So if you simplify this, you will get V of f is equal to Vc square by 4 m of f into h of f minus fc plus h of f plus fc plus ac square by 4 into m of f minus 2 fc h of f minus fc plus m of f plus 2 fc into h of f plus fc. So this is the output of V of t or V of f. So if you pass this, so here it consisting of first term represent the scaled version of the desired message signal. See, because we know that message signal is represented as h of f minus fc plus h of f plus fc, m of f into. So m of f, it is the message signal. So scaled version of desired message signal, and it can be extracted by passing the above signal through a low pass filter. If you pass that through a low pass filter, you will get V naught of f. So V naught of f is equal to AC square by 4 m of f into h of f minus fc plus h of f plus fc. So at last we will get the message signal, that is m of t. So this is how we can demodulate the VSB signal, that is vestigial sideband signal. So this is about the VSB. So what is VSB signal? The frequency domain description of VSB signals, generation of VSB signals, and demodulation of VSB signal. And next we will see frequency translation. What is this frequency translations? See here, uh, this block diagram of frequency translation consisting of a product modulator and bandpass filter. So the input for the product modulators are S1 of t and the C of t or AL cos of 2 pi FLT and the output of that is represented as S1 of t, and then pass through the band pass filter. The output of that band pass filter will get a modulated wave S2 of t with the frequency Fz. See, what is the frequency translation? Frequency translation is very commonly used process in many communication systems. It is necessary to translate the modulated wave upward or downward in frequency so that it occupies a new frequency band. So the above figure shows the block diagram of frequency translator. It consists of frequency multiplier followed by the band pass filter. Frequency multiplier multiplies the modulated signal and a locally generated sinusoidal wave. See here, this is the spectrum. So it is having a bandwidth of 2W, and here, so upward and downward of frequencies. So upward conversions, F2 will become F1 plus FL, and FL is equal to F2 plus F1, and downward conversion will become F2 is equal to F1 minus FL, and F1 FL is equal to F1 minus F2. So here mathematical representation of this frequency translation. Let us consider the DSPSC wave where S1 of t is equal to m of t into cos 2 pi fct. It is the input. S dash of t is equal to S1 of t into cos 2 pi flt. It is the flt. We know S1 of t as m of t into cos 2 pi fct into cos of 2 pi flt. So it is cos A, it is like cos A into cos B. You will get half m of t cos of 2 pi fc minus fl into t plus half m of t into cos 2 pi fc plus f1 into t. The output of the filter is given by S2 of t is equal to half m of t into cos 2 pi fc minus fl into t, where here this fc minus fl is shifted to f naught. It can be written as f naught. So half m of t into cos 2 pi f naught t. It is the output of S2 of, that is means S2 of t. This is the frequency translation. About the frequency translation. Next, this is the last topic in this module 1. It is frequency division multiplexing. So what is multiplexing? Multiplexing is nothing but it is the transmission of two or more signals in a single channel. We'll call it as a multiplexing. There are two types of multiplexing. One is the time division multiplexing and another one is the frequency division multiplexing. So in time division multiplexing, each signals are separated with respect to the time. In frequency division multiplexing, each signals are separated with the respect to frequencies. This we'll call it as a frequency division multiplexing. So it is more efficient communication systems can be obtained if a station transmits more than one message on the same carrier and on the same channel, or number of transmitters are transmitting simultaneously on the same channel. This process is called as multiplexing. So the figure shows the block diagram of a frequency division multiplexing. It shows the block diagram of frequency division multiplexing. And here the input messages assumed to be low pass type are passed through the low pass filters. Here we are going to assume the input messages are low pass, low frequencies, and that's why what we will do, we are going to pass through the low pass filter so that it only selects the low frequency signals. So input messages assumed to be low pass type and are passed through the input low pass filters. This filter's actions removes high frequency components that do not contribute significantly to signal representation but may disturb other message signals that shares the common channel. So the filtered message signals are then modulated with necessary carrier frequencies with the help of modulators. The most commonly method of modulation in FDM, that is frequency division multiplexing, is single sideband modulation, which requires the bandwidth that is approximately equal to that of original message signal. The bandpass filters following the modulators are used to restrict the band of each modulated wave to its prescribed range. The output of the bandpass filters are combined, which forms the input to the it forms the input common channel. So this all the output of all the bandpass filters are passed through a single channel, that is common channel. At the receiving end, bandpass filters connected to the common channels separate the message signals on the frequency occupies basis. It means how it is depend upon the frequencies. Finally, the original messages are recovered by individual demodulators. So after recovering the demodulators with the help of locally generated carrier signals, so the output of the demodulators are passed through the low pass filter. What the low pass filter will do, it only selects the low frequency signals and it rejects the higher frequency. Here low frequency signals are nothing but they are the message signals. So the output of the low pass filter contains the message output, that is M of t or M1 of t, M2 of t and M3 of t, like this. So the bandwidth required is equal to the bandwidth of the message signal here. So this is about the frequency division multiplexing. So this is how we are going to transmit two or more signals in a single channel to the receiver side. So these are frequency translations. This is about the frequency translations and frequency division multiplexing. So next we'll discuss some of the multiple choice questions related to today's session. Dash is the process. First question. Dash is the process where a part of the signal called a vestige is modulated along with one side band. Vestigial sideband modulation, AM, DSBSC, none of the above. So answer for this question, it is option A, that is VSB modulation. Second question. To generate the VSB modulate wave by passing DSBSC modulated wave through dash, sideband shaping filter, low pass filter, high pass filter, none of the above. The answer for this question is option A, that is sideband shaping filter. Third question, time division multiplexing and frequency division multiplexing are used to multiplex multiple signals into a single carrier. options false or true. The option solution for this, it is B, that is true. Next, question 4. FDM is an analog multiplexing technique used to combine analog signals, digital signals, both analog and digital signals, alternatively passes analog and digital signals. So answer for this question, it is A, analog signals. Next, fifth question. Frequency division multiplexing is based on orthogonality. Is it true? False? So solution for this, it is A, option A, true. Next, sixth question. In frequency division multiplexing, if 5 signals are to be multiplexed, at least dash carriers each of a different frequency must be modulated. 1, 5, 6, 10. Solution is, it is option B, that is 5. Next, seventh question. Frequency division multiplexing uses dash to prevent modulated signals from overlapping. Physical hardware devices, carrier frequencies, guard band, demultiplexers. Solution for this, it is option C, guard band. Question 8 and last question. In frequency division multiplexing, the dash signals can all have the same frequency range. Modulating, carrier, modulated, both A and B. So answer for this question, it is option A, modulating. So these are the some of the MCQ. Okay, two more questions. Ninth question. The FDM, frequency division multiplexing demultiplexers, uses a series of dash to decompose the multiplexed signal into its constituent signals: guard bands, filters, repeaters, amplifiers. So answer for this is option B, filters. Next last question, 10th question. The application of frequency division multiplexing. So options are TV broadcasting, AM and FM radio station, cellular telephones, all of the above. So answer for this, it is D, all of the above. So these are some of the multiple choice questions related to this session. And this is the MCQ test link. If you want to take a test through Google Form, you can go through this link and you can take a test, and even you can view the scores also. And these are the references. Through these references, we have made this with these references, or these are the which helps us to make this sessions. So thank you. I thank Chairman Dr. Rangaraju sir, HODs, moderators, and content developers. Thank you.